A cruise ship the length of 3 football fields is backing away from a dock in Southampton. No tugboats. No thrust from bow to stern reversing. The two-stroke diesel engines below decks never stop turning, never change direction, never even slow down in any meaningful way. And yet, somehow, 30,000 tons of steel is gliding backward. Look at the propeller and you'll see the obvious answer sitting right there in the water. The blades must be spinning the other way. That's what almost everyone assumes. A propeller is a screw. Reverse the screw. Reverse the ship. Simple, except the shaft is still turning in exactly the same direction it was 5 minutes ago. The engine hasn't reversed at all. A sensor on the bridge would show the exact same RPM, the exact same rotational direction, the exact same everything you'd have measured 5 minutes earlier when the ship was moving forward at full cruising speed. What actually changed is hidden inside a chunk of bronze roughly the size of a delivery van, bolted to the end of that shaft, sitting underwater, spinning at more than 100 revolutions per minute. That chunk of bronze is hollow, and inside it is a working hydraulic machine, pistons, valves, sliding rods, quietly rearranging the geometry of the blades while the whole thing spins, submerged, unseen, doing its job in total darkness a few meters below the waterline. Think about what that actually demands. You need to move solid metal parts, precisely, on command, inside a chamber that never stops rotating, sealed against seawater at real pressure, and completely inaccessible without hauling the entire vessel out of the water. No wires can safely cross that boundary. No simple lever can reach in from outside the hull. Whatever solves this problem has to live entirely inside the spinning object itself. Self-contained, self-lubricating, reliable enough to run for years without a single human hand ever touching it. By the end of this video, you'll understand how a ship reverses direction, holds a precise position against wind and current, and saves enormous amounts of fuel, all without its engines ever changing speed or direction. You'll understand how oil travels the length of a shaft longer than a football field without ever leaking into the ocean. And you'll understand why almost nobody outside of a shipyard has ever seen the machine that makes all of it possible. The first explanation people reach for is scale. A ship's propeller just looks like a bigger, tougher version of a boat motor's propeller. Same idea, thicker metal, more horsepower behind it. And there's truth in that. The blades really are cast from nickel aluminum bronze because saltwater is relentless, corrosion never sleeps, and a fixed shape does generate thrust exactly the way a smaller one does on a fishing boat. Some of the largest propellers ever poured weigh well over 100 tons and stretch past 10 meters across, cast in a single continuous pour that takes days just to cool without cracking. That's a genuinely impressive feat of metallurgy. But scale alone doesn't explain reversing 30,000 tons without touching the engine. A bigger version of a fixed blade is still, mechanically, a fixed blade. It has one shape, one pitch, one direction of useful thrust. It can't change its mind mid-rotation, no matter how many tons of bronze you pour into it. The second explanation is that the engine itself must run in reverse. This one is closer to true for some ships. The massive, slow-speed two-stroke diesels used on many container vessels genuinely can be stopped, held at zero, and restarted spinning the opposite way. An operation that takes real skill from the engine room and several tense minutes while the ship coasts forward on pure momentum, carried by tens of thousands of tons of inertia with no thrust pushing back against it. But that process is slow, mechanically brutal on the engine's bearings and injection timing, and completely useless for anything requiring fine control. Picture trying to ease a 400-meter hull sideways into a narrow berth in a crosswind using a maneuver that takes 3 or 4 minutes to even begin responding. If you needed to nudge a ship 2 meters to the left while holding position against a current, you would not want to be shutting down and restarting a 9-story-tall diesel engine to do it. You'd need something that responds in seconds, not minutes. The third explanation, and the one that gets closest without quite landing, is the gearbox. Many ships, particularly those with faster turning, medium-speed engines rather than the giant slow-speed diesels, route engine power through reduction gearing before it ever reaches the propeller shaft, and some of that gearing genuinely can reverse the direction of rotation independent of what the engine itself is doing. True enough, as far as it goes. But a gearbox lives up near the engine room, dry, accessible, serviceable by a technician standing on a solid deck. It explains nothing about why the propeller itself, the one part of the entire drivetrain sitting permanently underwater at the very end of the ship, sealed away from every human hand, needs to be hollow. If the direction change happens safely up at the gearbox, why does the hub, meters below the waterline, have a cavity machined into its very core? That question is the door. Walk through it. Here's the claim that sounds almost impossible. On many of the largest ships afloat, the propeller blades aren't fixed to the hub at all. Each one can rotate independently around its own route, like a screwdriver bit twisting in a socket, changing its pitch, the angle at which it bites the water, anywhere from full ahead thrust through neutral and into full reverse, all while the shaft keeps spinning in exactly one direction, at exactly one speed, indefinitely. This is called a controllable pitch propeller, and the mechanism that drives it lies entirely inside that hollow hub and the hollow shaft behind it. No part of it is visible from outside. No part of it can be reached without disassembling the hub itself. Everything happens inside a sealed cavity that spends its entire working life underwater. Layer 1. How do you get hydraulic fluid, oil under real pressure, from a stationary pump inside the engine room into a hub that's rotating over 100 times a minute, without the whole system leaking into the ocean? You use something called an oil distribution box, mounted where the rotating shaft meets the stationary hull structure, usually right at the forward end near the reduction gear. Picture a garden sprinkler bolted to a spinning bicycle wheel, except the hose feeding it never twists, never tangles, and never leaks, no matter how fast the wheel turns. The oil distribution box does exactly that for a marine shaft. It's a rotary joint, sealed with precision carbon rings rated to spin at full shaft speed for years without replacement, that lets pressurized oil flow from a source that never moves into a shaft that never stops moving. Inside that same box sits a second, quieter safeguard, a mechanical emergency positioner that can lock the blades at a fixed, safe pitch if the hydraulic system ever fails, letting the ship limp home under what engineers call take-home power, instead of drifting helpless. It is, quietly, one of the more elegant pieces of plumbing in mechanical engineering, and it sits in a compartment most crew members walk past every day without a second glance. Layer 2. How does that oil actually travel the length of the shaft? Sometimes over 100 meters, longer than a football field, running from the engine room all the way out to the stern tube, to reach the hub at the far end. Not through a single tube. Marine engineers hollow out the propeller shaft itself and thread a second, smaller pipe inside that hollow, creating a pipe within a pipe. Two concentric tubes nested one inside the other along the shaft's entire length. Oil flows down the outer channel to push the blades one direction, and returns up the inner channel to release them the other way. Two separate hydraulic pathways sharing the same drilled-out steel, never mixing, both spinning together at the same speed as the shaft around them. Even the space inside the hub cavity that isn't actively pressurized for pitch control stays filled with oil at a gentle standing pressure, just to lubricate and protect the moving parts sealed inside. It's the plumbing equivalent of running two independent water systems through one twisting artery, then keeping the whole artery bathed in its own protective fluid. Besides. Layer 3, and this is where the actual blade movement happens. At the hub end, that inner oil pressure pushes against a piston sitting inside the hollow core of the propeller boss. But a piston only moves in a straight line, forward and back along the shaft's axis. Blades need to rotate around their own individual routes. So, engineers built a translator between the two kinds of motion, a sliding collar called a crosshead, carrying a set of pins that ride inside angled slots cut into the base of each blade. As the piston pushes the crosshead a few centimeters fore or aft, often less than the length of your hand, sometimes only 10 or 20 centimeters of total travel, those pins drag through their angled slots and force each blade to twist on its own axis, all 4, 5, or 6 blades rotating in perfect unison, driven by one small linear nudge multiplied through geometry into a full 45-degree arc of blade angle. The steeper the slot is cut, the faster the blades respond to a given push, at the cost of needing more force behind that push. It's the same trick as a car window crank, or the mechanism inside a click pen, a small motion, converted through angled geometry into a much larger one, just run at industrial scale, sealed in bronze, and permanently underwater. Layer 4 closes the loop, and it's the part almost nobody thinks to ask about. How does the bridge crew, standing dry and comfortable 300 meters away, know what angle the blades are actually sitting at right now? A second, thinner rod runs back through the very center of that hollow shaft, mechanically tied to the crosshead, reporting its exact position the entire time, riding inside the innermost of the nested tubes we just described. Move the crosshead, and that rod moves with it, feeding a live position signal all the way back to a gauge on the bridge, sometimes through a mechanical linkage, sometimes converted to an electrical signal partway along. The captain isn't guessing. The ship is telling them, in real time, precisely how much bite the blades currently have on the water, a nervous system built entirely inside a machine that never once stops turning. Once you see that hidden machine, a dozen things about ships you've watched your whole life suddenly make sense. A ferry that swings into a slip, nudges sideways against a current, and settles against rubber fenders without a single tug assisting. That's controllable pitch, letting the crew dial in tiny amounts of forward or reverse thrust in seconds instead of minutes. A research vessel or icebreaker that holds an exact position over one fixed point on the ocean floor for hours, compensating instant by instant for wind and swell. That's the same hub, driven by a computer instead of a hand on a lever, making hundreds of micro-adjustments an engine could never make on its own. Even the old ocean liner QE2, crossing the Atlantic decades before any of this was computerized, relied on the same basic hydraulic principle in her own variable pitch propellers. Proof that this isn't some recent innovation but a solution engineers have trusted for generations. There's a fuel story hidden here too. A ship's diesel engine runs most efficiently at one particular speed. Every time you slow it, speed it up, or reverse it, you burn fuel less efficiently and put wear on components designed to run steady. A controllable pitch system lets the engine sit at its single most efficient RPM for the entire voyage, while the hub does all the maneuvering. Work, the propulsion equivalent of a hybrid car's engine, humming along at one ideal rate while the transmission handles the actual variability of traffic. And there's a safety detail buried in that hub that reframes the whole system. The oil cavity inside the boss isn't just pressurized to move the piston. It's kept at a static pressure slightly higher than the surrounding seawater at all times, even when the ship is doing nothing at all. That constant outward pressure exists for one reason. If a seal ever begins to fail, oil leaks out into the ocean before seawater can leak in. A tiny, deliberate pressure imbalance, maintained around the clock, exists purely to make sure that a machine full of moving parts, sitting permanently underwater, fails outward instead of flooding inward. Step back far enough, and this hub stops looking like a propeller part and starts looking like something else entirely. A sealed, self-contained hydraulic computer, with its own plumbing, its own feedback nerve, and its own fail-safe logic, built to survive years underwater without ever being opened. It's not an accessory bolted onto the ship. It is, in a very real sense, one of the ship's organs, doing the job of a transmission, a steering system, and a nervous system all inside one bronze casting most passengers will never lay eyes on. And that's the pattern worth carrying with you past this video. The biggest machines humans build are full of quiet, self-contained systems like this one. Mechanisms doing extraordinary work in total silence, in places nobody thinks to look, simply because looking was never required for them to work. Somewhere on almost every large ship at sea right now, one of these hubs is turning, adjusting, reporting back, and no one on board is thinking about it at all. If that's the kind of hidden machinery you like having explained to you, this is exactly what Discovery Loom does, pulling apart the ordinary things around us until the extraordinary engineering underneath is impossible to unsee. Stick around for the next one.